105, square and cube roots. First, we'll look at some examples of perfect squares. 1 squared equals 1, 2 squared equals 4, 3 squared is 9, 4 squared is 16, and 5 squared is 25. So this list of numbers, 1, 4, 9, 16, and 25, these are perfect squares. So our definition of a perfect square is a number that is made by squaring a number. So all of these are made by squaring a number. They're all perfect squares. In addition, there's a really cool visual component to this. So I can make each of these numbers, 1, 4, 9, 16, and 25, I can make each of them as a square. So 4 I can make as a square that is 2 units by 2 units. 9 I can make as a square that is 3 units by 3 units. So numbers that are not perfect squares, you cannot build and make into a square. You might be able to make them into a rectangle, but they're not a square. So perfect squares are actually visually a square. So next we have anatomy of a square root. So if I'm looking at square root of 9, this square root part, we actually have a name for that. It's a radical sign. And we don't just have square roots, we have cube roots also. We'll look at those in a little bit. The number inside is the radicand. And just to kind of wrap up this page, let's go through and write down 3 times 3 equals 9, 3 squared equals 9, square root of 9 equals 3. So 3 is the square root of 9, and 9 is a perfect square. Just kind of to summarize everything that we've done on this page. Next, we'll look at solving equations by using a square root. So we need to note that just like multiplication and division are inverses and adding and subtracting are inverses, that squares and square roots are inverses. So an inverse operation, inverse operations is something that undo each other. So if I have 3 times a number and then I divide it by 3, I go back to that number. Those are inverses. So squares and square roots are inverses. It's really important when we're solving equations that each operation has something that can undo it so that we can actually solve. So for these two examples, because x is being squared, I am going to use the inverse and I will square root on both sides. So if I have x squared and I take a square root, we know that those operations undo each other. We're left with x, and the square root of 144 is 12. But we're not quite done yet. So when we are taking the square root of a positive, when we're solving and we're square rooting a positive, we're going to have something kind of interesting that happens here. So one solution is 12, because 12 times 12 is 144, but we have a second solution. Negative 12 times negative 12. Negative times negative is positive, so that's also 144. So if we're solving and we square root a positive, we are going to get 2 answers. So for this problem, x is actually going to equal 12 or negative 12. So we're going to write that as a plus or minus. And so that's because we were solving an equation that had a square root and it was positive. So if I had something like just the square root of 144 by itself, with no symbols, no x's, anything around that, that's just a positive 12 only. But if I have x squared equals 144, then we're going to have x equals plus or minus 12. And that's because I could square a positive number or a negative number and get that 144. So if we're not solving an equation, it just has one value. If we're solving an equation that has x squared, we're going to have 2 values from that. So our second problem will do the same trick. We will square root both sides, but on this one I have a square root of a negative. So when I have a square root of a negative, there is no real solution. And let's think through why this is. We know that a perfect square is made by multiplying a number by itself, but the only way to get 144 is to multiply a negative 12 times a positive 12. These are not the same factor. And so they don't work. I don't have a number that I can multiply by itself and get a negative. So if we are solving and the square root is negative, there is no real solution. Next, we'll look at non-perfect squares. So an example of a non-perfect square would be the square root of 6. So there's a couple different ways I can tell this is not a perfect square. 1 squared is 1, 2 squared is 4, 3 squared is 9, 16, 25. These are our perfect squares. And 6 falls between a couple of them. 6 is between the 4 and the 9. So because it's not on my list, it's not going to be a perfect square. Another way I can tell is by actually trying to build it. So when I use 6 tiles, 1, 2, 3, 4, 5, 6. So this is a representation of 6. I have 2 on one side and I have 3 on the other. It is not a square. So when I want to find the value of a non-perfect square, I'm going to have to use a calculator. Let's look at one more really quick and make sure we understand it, and then we'll go ahead and we'll use a calculator and we'll find the value of both at the same time. So another one that I could use is 2. So let's look at square root of 2. So square root of 2 would be between the 1 and the 4. 2 is not a number on my list, so being not a number on the list is one way you can tell. The other way is if I go to draw this, to get 2, I end up with a 1 by 2 shape. That again, 1 times 2 is 2. I'm not multiplying a number by itself, and it is a rectangle, not a square. Squares would have to be the same on both sides. So square root of 2 is not going to be a perfect square either. So that's another non-perfect square. So what we know, according to the lesson that you might read online, is that they want you to approximate these square roots. And it involves a lot of guessing and checking. So I don't really think that that is worth our time. What I do think is worth our time is kind of looking at this list of perfect squares and being able to tell what it's between. So I know that the square root of 1 is 1, and the square root of 4 is 2. Square root of 9 is 3. So when I'm looking at the square root of 6, since that's between 4 and 9 here, it's going to be between the square roots, 2 and 3. So I know that this is going to be between 2 and 3. And similarly, I can tell that the square root of 2 must be between 1 and 2. So I would like you to be able to do that. However, the rest of it you're going to do on a calculator. So when I go ahead and work out square root of 2 on a calculator, I get 1.4142 and on and on and on. It's irrational because there's no pattern. It goes on forever. It does not terminate or repeat. And I really want to round that probably to the nearest tenth of the nearest hundredth. So if I'm looking at hundredth, the 4 is my tenths place, the 1 is my hundredths. The number after that is less than 5, so I'm going to leave it as 1.41, just to give us a little review of rounding. So when I take the square root of 6 on a calculator, I get 2.4494, on and on and on. So that one's going to be irrational as well. And if I want to do 2 decimal places on this one, I would have 2.45. Because after the 4 is a 9, I want to round that up to a 5 instead. And we use those squiggly equal signs to show approximately equal to. A lot of information in this section. So understanding cube roots. So if we can have perfect squares, we can also have perfect cubes. So to just give you guys a couple of examples, 2 times 2 times 2, that would be the same thing as 2 cubed, which is 8. And so when I take the cube root of 8, it is going to equal 2. 3 times 3 times 3 equals 3 to the third power, or 3 cubed. 3 times 3 is 9, times 3 is 27. And so the cube root of 27 is going to equal 3. 4 times 4 times 4 will equal 4 cubed, which is 64. And so the cube root of 64 equals 4. We're going to do one more. 5 times 5 times 5 is 5 cubed, which is 125. And so the cube root of 125 equals 5. These are a lot harder to just look at and know. So sometimes you're going to have to guess and check on a calculator. So if you want to know the cube root of, say, 343, you might have to just start guessing. You might try 8 to the third power or 9 to the third power. You might just keep guessing. If it's too big, then you'll guess a smaller number, but you'll be able to go through and figure them out that way. Let's also add in 1. 1 times 1 times 1 equals 1 cubed, which is still 1. And so the cube root of 1 equals 1. So these are our cube roots over here. That's what we're doing. And these are our perfect cubes. I really feel like we should almost do this. Now we're going to solve equations using cube roots. So if multiplication and division are inverses, adding and subtracting are inverses, squares and square roots are inverses, then cubes and cube roots are inverses. So if I have x cubed, then I need to do a cube root on both sides. So then I'll have x equals, and I'll have to figure out what number times itself, I gotta have 3 factors, would equal 343. So first I'm gonna use my calculator and do 9 times 9 times 9. That gives me 727, way too big. And this is an odd number, so I'm not gonna try 8, I'm gonna go ahead and jump to 7. 7 times 7 times 7, when I work it out on my calculator, equals 343. And so I know that x must equal 7. Now let's think about a negative 7 times a negative 7 times a negative 7. 2 negatives would make a positive, times another negative would equal a negative. So on this one, I cannot have more than one answer. If I was to multiply a negative 7 3 times, I would get negative 343. So for cube roots, when we're doing cube roots, there's going to be only one answer. And I can have negative or positive. So on the second one, if I cube root both sides, and I have to figure out what number times itself 3 times would equal a negative 1, I know I'm going to have a negative answer. So these signs are going to always match. Maybe we should make that note also. Signs match. So on the second one, x is going to equal, well, the only way to get a 1 is to keep multiplying ones. So negative 1 times negative 1 times negative 1 will equal negative 1. And so x equals negative 1. And again, our signs are going to match. And this one, the numbers match too. But our signs match. If we start with a negative and we do a cube root, we're still going to have a negative. Now we move on to the examples that are going to help get you ready for the quiz. So example 1 is really straightforward. We're just finding the square roots. Square root of 100 is 10, because 10 times 10 equals 100. On this one, because of this negative sign here, we write down a negative. It's not inside the square root. That would be a problem. It's outside. And then 7 times 7 is 49, so this will just be negative 7. This one has a negative in front as well, so we'll have negative 1. 1 times 1 is 1. And we can't take the square root of 0. It's just 0. Example 2 is asking us to solve each square root equation. So for this first one, I know I need to square root both sides, and that's what I'll be doing on each problem. And, oh, we have a square root of a negative, so this one will have no real solution. On the second one, when I square root both sides, because I'm square rooting a positive and I started out with x squared, I could have squared 2 different numbers, a positive or a negative. So this is going to be plus or minus, and 6 times 6 is 36. So remember, 6 times 6 is 36. And negative 6 times negative 6 is also a positive 36. On the last one, or next one, I guess I should say, when we square root both sides, we're square rooting a negative again. So there's no real solution. I can have a negative outside of that square root, but not inside it. And last one, square root both sides. I have a positive again, so we'll get a plus or minus on our answer, plus or minus 1. For example 3, it says state whether the square root is rational or irrational. If irrational, then approximate the square root of 5 to 1 decimal place. So we're looking at the square root of 5. So I cannot build a square out of that. And if I think about my list of perfect squares, let's make that little list again. It's really good to have one of these handy when you go ahead and are ready to take the quiz. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 25, 36. 5 is not on our list anywhere. It's between the 4 and the 9, square root of 5 is. So those square roots equal 2 and 3. So the square root of 5 is going to be between 2 and 3. So I'm going to go ahead and use a calculator. When I do square root of 5 on a calculator, I get 2.23606797775, and it goes on and on forever. So this doesn't terminate because it goes on forever, and there's no repeating pattern. So I can say that it's irrational. And they want me to approximate to 1 decimal place. So square root of 5 is approximately equal to 1 decimal place would be this right here, and after it is a 3, so I would not round up. I would leave it as 2.2. For example 4, we're solving the cube root equation, and they're going to throw some fractions at us. So I want to think about my perfect cubes over in the corner here. I know 1 cubed is 1. 2 cubed, 2 times 2 times 2 is 8. 3 cubed is 27. 4 cubed is 64. 5 cubed, I'm just continuing until I see all the numbers that I need here. So 64, the next one would be 125. 5 cubed is 125. So now I have kind of a little cheat sheet to look at over here. Again, it is nice to have a list of these handy when you're taking your quiz. I might go up to 10 cubed. So because I have x cubed, I'm going to cube root both sides. So x equals, remember on this one my sign matches, I don't have two answers. My cube root of 8, looking at my list, is 2. And my cube root of 27 is 3. So I get 2/3. On the next one, cube root again. So x equals, and then again I just have to look at my list. Cube root of 125 is 5. And my cube root of 64 is 4. So 5/4. And last one, cube root. This one I'm cube rooting a negative, so I'm going to have x equals a negative. Cube root of 1 is 1. Cube root of 64 is 4. And for our last example, example 5, a square garden is approximately 115 square feet. What is the approximate length of one side? Approximate to the nearest hundredth of a foot. Well, we know, if we think back to 9, that if we have 9 square feet, it's going to be 3 on both sides, and we could get that because the square root of 9 equals 3. So for this problem, in order to figure out the length of each side, I'm going to have to take the square root of 115. So again, your book wants you, or your online lessons want you to use like guess and check and common sense and kind of approximate this. We're just using a calculator. So it gives me 10.7238, and it goes on and on forever. It's irrational. So I'm going to write 10.72 because a 3 comes next. Maybe I should write that out. 7238052 ... So when I round, because a 3 is the next one and 3 is less than 5, I leave it as a 10.72. If you still have questions on any of this, please reach out. This was a really long lesson. There's a lot of information in this, and it's been a while since we worked with squares this year.